For my culminating project, I will be doing Module 14, Temperature and Reaction Rates. During this PowerPoint, we will be answering the question, why does reaction rate increase with increased temperature? We will be doing this using collision state theory and transition state theory, and then we will look at a reaction at the molecular level, and then we will do the rate of reactions at different temperatures and compare those. Let's talk about collision theory. It explains why reactions happen at different rates and how the rate of reaction depends on how often particles collide. But it is important to know that they can collide without reacting. This is because there are a few factors needed to react. First, they need to collide. This is quite obvious. Second, they need enough energy to break the bonds so that they can reform new bonds for the products. And third, they need proper orientation, meaning that they need to collide together at a certain spot for it to work. Now let's build on the last points. To start off, they must collide. Two molecules must collide. This means that they have to come close enough to break the current bonds and new ones that the products need. If one molecule, we can call it X, doubles, or one molecule that we'll just call Y, doubles, then the frequency of XY collision doubles because it is proportional. The next statement is that they need enough energy. Well, a collision of two molecules needs enough energy to break the chemical bonds so that new bonds can be formed in the reaction. The molecules need to move quick enough so that the kinetic energy is increased so bonds can break when they collide. The minimum they can move to have a reaction is called activation energy. The third statement is proper orientation. This is simple. The molecules need to line up at the right spot so that bonds can break and reform properly. Now we'll talk about collision theory and temperature. The rate of reaction depends partially on collision frequency. Temperature has a big impact on collision frequency. Increased temperature means increased average velocity of particles and increased average kinetic energy. This increases particle collisions because the particles move quicker. They will also have enough energy to have a good collision due to higher activation energy. Decreasing the temperature slows particles, slows the average velocity and the average kinetic energy, and slows activation energy. This slows down the reaction, and that is why people do it to keep food good for longer. This graph is great to show collision theory. On the y-axis, it is the number of particles, and the x-axis is the energy. The blue area is the number of particles represented by the area under this part of the curve, and they don't have enough energy to react. Then the green area is the part of the curve where there is enough energy to react, and the green line is the activation energy. Increasing the temperature increases the activation energy, so the green area will increase, meaning it can react because it has enough energy. When decreasing temperature, energy is decreased, so the green area is incredibly small because there's not enough energy to react. Now we will talk about transition theory. It is an unstable intermediate and focuses on an activated complex that forms during an energetic collision. It says that in between the state where molecules are reactants and the state where molecules are products, there is a state called transition state. The reactant bonds are partially broken and product bonds are partially made. It explains the rate of reactions for elementary chemical reactions and assumes quasi-equilibrium between activated transition state complexes and reactants. Here's a fun graph to help show it. The y-axis is PE, which is potential energy. The x-axis is the extent of the reaction. This shows how H2 plus I2, which are the reactants, have a higher potential energy than 2HI, which are the products. Then you can see the saddle point, or at the top of the orange curve, which is the intermediate and transition state. During this time, H2 and I2 look like the diagram on the far right towards the top. They can go either way, back to H2 and I2, or forward with the reaction to become 2HI. This is a transition state. Now we'll look at transition state theory and temperature. It fails at high temperatures, as some say, as it assumes the reaction would go over the saddle point on the potential energy surface. The reaction rate is seen by looking near the saddle point, which has activated complexes nearby of its potential energy surface. The complexes use kinetic theory to calculate the rate of conversion when the activated complexes turn into products. Higher temperatures mean that the molecules are more complex, making transition states far from the lowest saddle point in terms of energy. I could not find very information or examples of temperature and reaction rate, so I'm going to show a couple of graphs instead. One is the speed of ants as a function of temperature. As you can see on the graph, as the temperature increases, the speed increases quickly. The physicist Harlow Shapley on Mount Wilson above LA, where he was engaged in measuring the size of our galaxy, studied ants. The ants that he studied were active both in the day and the night, which means a larger temperature range could be studied. And as you could see, as the temperature increased, the speed also increased. He also said that the body mass did not matter and that this could be neglected. This really confirms what we were talking about earlier when we said that increased temperature increases reaction rate. The next one is the change in rate for a 10 degrees Celsius increase in temperature. The rate in bracket of T2 over the rate of T1 equals E2. So that means the change in rate for 10 degrees Celsius increase in temperature is 2. As in the speed doubles for every 10 degrees Celsius increase in temperature. This next one is the dependence of the growth rate of E. coli on temperature. You can see from 48 degrees Celsius to about 39 degrees Celsius, the rate is steady but very quick. Then you can see how it's almost like an ideal rate between 39 degrees Celsius and 21 degrees Celsius. And then it rapidly goes down from 21 degrees Celsius to 13.5 degrees Celsius. The growth rate is plotted versus the inverse of the temperature, which is an Arrhenius plot. You can also kind of see how in the middle range where the dependence looks linear. This makes sense with the Arrhenius rate law. And then here are the references. I used 4 different references, and one reference is where I got all of the examples that I just said from. I think learning from graphs is equally as important as learning from equations because graphs show real-life data and we can learn greatly from that. I think there is a strong importance in learning from graphs and seeing real-life data plotted so that we can see not just an equation of how different temperature changes reaction rates, but an actual real-life data set. And that's it. I hope you learned something from my presentation/tutorial.